Oh, there it goes. Hey, you look good. You're so good looking. Okay.
From this angle, it's like X-ray.
All right, here we go. Copy. I'm copying the link. I'm almost done. Sorry, it's long. I'm going to be faster one day. I'll be like Riley. I'll be as fast as Riley on the stream. You're pretty fast, right? Are you on Twitch? No. What do you do? Anything? Oh, I thought you said you were doing. You used to? Oh, you did. Okay. Okay. Maybe you will again. Make some money, huh? Okay. And all exam review. Okay. Oh, and so all I have to do is click enter, and then the link is automatically linked. I just never enter that one time. Okay. Here we go. Live. Here we go. Let's begin. All right. So, okay, so we're beginning with chapter 15, and we did cover everything this time, so nothing to leave out. Just want to try to make sure you know the definitions of all the words, and then in each case where it says you should be able to explain something, you should be able to explain that concept clearly, because there will be questions related to that concept. Okay? So let's get started. Okay, so, oops, you know what, I just realized, yeah, I might have signed the wrong section. Should have been the final exam. Yeah, you signed the setting on it. There you go. I would know that, but final exam, study guide. Okay, here we go. Final exam study guide. And I can pull this sideways and it gets bigger, and now I can match better than I used to. Okay, cool. So the first term is the Galactic Fountain. And you might remember the name Bob Benjamin associated with that. The Galactic Fountain was a concept that allowed matter from one part of the Milky Way to move to another part of the Milky Way. And no one had ever figured that out before. Bob Benjamin saw clouds of gases both streaming away and towards the Milky Way. He wrote a paper and submitted it, and it was reviewed by Lyman Spitzer, who was a very famous physicist. So the Galactic Fountain is a mechanism for mixing the gases of the Milky Way. How does it start? Anybody remember? It starts with a supernova, or some kind of a blast that sends matter away, and then why does it fall back down? Because of gravity. Okay, so that's it. That's it. Yeah. What was that? Bob Benjamin. Bob Benjamin. Yeah, you know, the names aren't quite that big a deal, but Spitzer was pretty famous. Spitzer was more famous. The Milky Way is our galaxy, and when I say Milky Way, I think you should immediately, I think we're going to come to it in a minute, but you should know the parts of the Milky Way, right? Where do we live? Which part of the Milky Way do we live in? The spiral arm. The disk. Yeah, we live in one of the spiral arms. That's right. We live in one of the spiral arms. The Cygnus Orion Cygnus spiral arm. We're across from the Perseus spiral arm. You don't have to know that though. But we're in the disk. What are the other parts of the Milky Way? The bulge in the middle and the halo. Those are the three big parts. You should have a clear sense of how big the parts are. How big do we say the disk is from one side to the other, the diameter? 30 kiloparsecs, or 100,000 light years. That's the diameter. The bulge, how big is the bulge? 10 kiloparsecs in diameter. How big is the halo? 30 kiloparsecs in diameter, but it's a sphere, a spherical halo. Okay, so those are the parts and the things. About how many stars are in the Milky Way? That would be another question I could ask you. 400 billion is a good estimate. We say between 200 and 400. That's been changing, by the way. When I first started teaching this course, it was only 100 billion. Not kidding, right? So in just 7-8 years, it's changed from that to now we think about 400 billion. As technology improves, we can count better. We have a better estimate for that actual number. Okay, so Caroline, William Herschel, why were they important? What did they do? They gave us the first picture of our Milky Way. What does it look like? It is a flattened disk. How did they do that? They counted stars, and they showed where the stars were located. They made a picture from, well, William was the telescope maker. Caroline helped him
by looking carefully and making very careful pictures, images of the stellar location. So they found that the Milky Way was a disk, very small. I forgot the exact number. You don't have to worry. But what was the problem? Why did they not have a very good model of the Milky Way? What was their big flaw? The sun was the center of the distribution, and that's just wrong, okay? So then along comes Lewis, captain in the early 1900s, and he also counted stars, but he did a better job. What did he do that was so much better than the Herschel siblings? He took photographs, and from the photographic negatives, he could not only see the positions very precisely, but tell their magnitudes. And so he made a beautiful picture, stellar map, and he came up with a size for the Milky Way that was too small. Was an oval shape, a flattened disk, similar to the Herschel's. But again, the sun is at the center, right? And so we know that there's a problem. If you just try to count the stars, they counted stars, and then we started to talk about this new fellow, Harlow Shapley. Instead of looking at individual stars, he focused his attention on the globular clusters. So let's stop for a second and ask, what is a globular cluster? What's special about it? It's a cluster of stars, thousands of stars, to hundreds, tens of thousands of stars, and it's globular, means the shape is a sphere. Okay, how did it get that way? Gravity. Over a long time, the stars that were born in that cluster gathered together into a spherical shape. So what do we know about globular clusters? Who's in there? Who's in the globular clusters? Old stars. Okay, lots of old stars. The stars that were young have already gone. They're left the building, right? They're not there anymore. So what's in a globular cluster? Lots of these old stars. How did they get so old? Well, we think that they were born about the same time as the Milky Way. And that means they're as old as the Milky Way, which is about 13.2 billion years old, 13.1, 13.2. How could they be that old and still be there? What kinds of stars can live that long? Red dwarfs, lots of these red stars. So globular clusters are going to have lots of red stars in them. So Harlow Shapley, instead of focusing on individual stars, focused on the clusters of stars. And he found that they made this giant spherical shape. There are only about 150 of them. He didn't even see all of them, but he could still see the shape of that the globular clusters were arranged in a spherical shape. And he said the center of that sphere must be the center of the Milky Way galaxy. Oh, he didn't know it was a galaxy, by the way, but the center of the universe, right? The center of everything should be the center of the globular clusters, and he was right. And so we give him credit for figuring that idea out. Instead of the individual stars, the globular clusters, which are not in the disk, but above and below the disk, gave him the correct idea. The sun is not the center, and that was what he's known for. He didn't quite get it right, but where is the center of the Milky Way? How far from us? 8 kiloparsecs from us. That's a number you're supposed to remember. Okay, so we mentioned the disk, we mentioned the bulge, and we mentioned the halo. Okay, so what's special about each one of these? Let's talk about what's special. What's special about the disk? What do you know about the disk? Well, that's where all the exciting stuff is happening, right? That's where the arms are. That's where all of the new stars are found, right? Where are the new stars? In the disk, right? And so because they're new, they're not the first generation stars. They're the second. No, they're not the second either. They're probably third, fourth, fifth, right? They're the higher generation. So what tends to be true about the stars in the disk? Do they tend to have just hydrogen and helium? Why not? They're not first generation, right? So they have metal content, right? The metallicity is higher. And what's the name that we give for them? Population 1, right? The stars that are in the disk are called population 1. They're younger stars, they have metal, and they're found in the disk. The bulge is, what's the difference between the disk and the bulge? The bulge is in the very center of the Milky Way, just that central part, and it's very dense. We talked about the density. You don't have to know numbers, But the idea is it's hundreds, if not 1,000 times the number of stars per unit, per volume as there are in the disk. They're much more tightly packed. So a lot of stuff happening there. There are even some new stars being born, but not nearly as many as in the disk. Okay, so what do you want to know? The bulge is where you have a huge concentration of stars. That's about it. That's what I would want to know, right? Very small. The halo is where we find the globular clusters. So there's no new stars there, but we do have the globular clusters, and the globular clusters are orbiting the center of the Milky Way on highly elliptical paths and in very different directions. They do not appear to be organized in any particular way. They're almost like buzzing bees, buzzing around the center of the Milky Way. Okay, that's what I think about. Then we get to the spiral. What's a spiral galaxy? The Milky Way. Hey, the Milky Way is an example of a spiral galaxy. A spiral galaxy has arms which are curved and go away from the center. The spiral arms of a galaxy, usually less than 4. 4 is kind of a typical number. Metallicity is a term that we just talked about. It's the metal content of stars. The first generation of stars do not have metal. They're only hydrogen and helium. But each generation enriches the next generation. So each generation will have a higher and higher metal content. We can determine the generation by the amount of metal in the star itself. Population 1 stars we just mentioned in the disk. Where do you find population 2 stars? In the halo, in the globular clusters. What do we say about them? Are they young or are they old? They're old. They're generation 1. They're first generation stars. Now, I didn't talk about it in this course, but has anybody ever heard of population 3 stars? Okay, so those are the very first stars that were created in the entire universe. And we've never seen them. We're just hypothesizing they exist, but you don't have to know that. I'm just curious if anybody has heard about that. Sorry, it's not on the list. Don't worry about it. Okay, so technically speaking, our Milky Way is not just a spiral. It's called a barred spiral. So what makes it a barred spiral? Instead of one center, the nucleus or the bulge here is extended, and the arms come out of the end of the bar. The barred spiral is similar to a spiral, but it's slightly different. Okay, not a big deal. Really just a name, nomenclature, right? Although we do want to talk about why it becomes a barred spiral, right? That's an interesting idea. Andromeda Galaxy, what's special about the Andromeda Galaxy? Why would you want to know that?
The closest galaxy.
The closest spiral galaxy, make sure you qualify, right? There's the other ones are the small and large Magellanic clouds, right? And they're much closer, but Andromeda is the nearest spiral galaxy. But what else? It's coming to visit, right? So in like 3 to 4 billion years, we will first start to feel the gravitational pull. And then eventually what will happen? They will merge, right? The Milky Way and the Andromeda Galaxy are going to merge into one. And you're supposed to know the name of the future galaxy. What is it called? Milkomeda, right? And this is funny. It's supposed to be funny. That's all. That's all. Okay, so we just mentioned Andromeda, and then much closer to us, we have the large and small Magellanic Cloud. Now, I didn't mention the word dwarf galaxy, but they are, in fact, dwarf galaxies. Anybody remember what that means? Smaller in size and in mass. They're both about 1/10 the size of the Milky Way. So they're little galaxies. They're orbiting, so they're called satellite galaxies. And anybody else know something interesting about that, right? There is I think we're coming up to it in the next chapter, right? But there's a layer of a stream of gas coming from each one of them, and it's hitting the Milky Way because it's being ripped off by the Milky Way. We call it the Magellanic Stream. Okay, I think there should be 2 of them really, but I've only heard Magellanic Stream. What is that? What are we talking about with O and B associations? Stars. O and B, what are those? Really bright, really young stars, right? They can only live a little while. They're the hottest, brightest stars that we have. And where are they forming? It's at the edge of the spiral arms, right? So when we see those, we know that's where new stars are being born. What will happen is they will blow up and then spread with their waves or supernova wave. They'll start a new round of new star development. So what we see is a wave going down the spiral arm that gets propagated by generation after generation of stars living along the edge of the arm. It doesn't happen all at once. There's a wave of star formation down the arm. We call that a spiral density wave. Okay? You don't have to know much more than that. Just you don't get stars all at once. It takes time to propagate down the arm. Sagittarius A, actually it should be A star, but SGR. I don't know why it says SAGR. It should be SGR. Sorry about that. Little mistake. But Sagittarius A star, what is that? Supermassive black hole at the center of the Milky Way. Okay. How big is it? Is it a little bit bigger than the sun or a lot bigger? It's 4 million times the size of the sun. It's huge, right? It's a supermassive black hole. Okay, Vera Rubin, her name is important because she watched the rotation of our galaxy. And she noticed, actually rotation curves of galaxies, and she noticed something really disturbing, that instead of slowing down as you go further away from the center, like planets would do when you go further away from the sun, they don't slow down. They keep the speed or maybe even go a little bit faster. And so as a result, she said, there must be more matter keeping them from flying away than we can see. She called this stuff dark matter. And what percentage of a galaxy would be made up of dark matter? 90% of the galaxy is made up of dark matter. So that's a huge amount. Can we see the dark matter? No, but we see the effect of the dark matter. So when we say dark matter, what do we say? It's matter that we can't see that exerts a gravitational force which keeps the galaxies from flying apart. If it wasn't there, then the galaxies at the edge of the, the stars at the edge of the galaxy would be moving too fast and they would escape. They're moving way too fast if they don't have dark matter. Okay, so the two candidates for dark matter that we talked about are the macho and the WIMP. Okay, so what does macho stand for? Massive, compact, halo object, right? So what would that be? What would a massively compact, that would be a black hole. So the first idea was, the dark matter is just a whole bunch of black holes. We can't see them, that's perfect. It really was a good idea, but one of the hypotheses that would come from that model is that as a black hole passes in front of a galaxy or other source of light, there would be a gravitational lensing, and you would see a flash of light every time that happened. So it should be, with all these black holes flying around, we should see those flashes appearing all the time, but they don't. And so this means there's a negative result there. We don't see the flashes, there are not black holes there. There may be some, but not nearly the number that we need to explain the dark matter. Okay, there's not 90% of the mass of our galaxy. So we ruled out macho. We're no longer thinking that's right, and we're left with WIMP. What's WIMP stand for? Weakly interacting but massive particle. And so that means it exerts a gravitational force, but we're hoping that it also interacts through the weak nuclear force, because if it does, there's a way for us to feel it, to sense it. And so if we do an experiment on Earth, right, or in space, we might be able to make these particles smash into matter and interact and make, some kind of flash of light or something that we can detect. So the goal is that if these particles interact through the weak nuclear force, then we will see something happen when we do the experiments. Yeah.
What's the rotation curve?
Rotation curve is the idea that we watch, you go away from the center of a galaxy, from the center to the edge of the galaxy. The speed of the stars is supposed to change, right? But in fact, the rotation curve means the velocity as a function of radius or distance from the center. So the further away you go, we would have expected it to go slower, but instead of going slower, it seems to maintain the same speed. And so that's not possible. It shouldn't do that. And so there must be more matter holding it in. It's going too fast, right? The stars at the edge of the galaxy should be the slowest, but instead they're going almost the same speed as the ones inside. All right, so we covered our vocabulary. Pretty good. Okay, that was fast. Let's see the idea. Okay, so be able to Okay, so there's Bob Benjamin. He wrote a paper about the Galactic Fountains, submitted it, and actually Lyman Spitzer thought it was really great. It was a cool idea. It was the first time anyone could explain how the material of a galaxy gets mixed. And it was a beautiful, simple explanation. Supernovas blast material out, gravity pulls it back in, but not to where it started. So it's a fountain. How has the model of the Milky Way changed? We kind of discussed this. Basically, everybody who tried to see the Milky Way saw that it was shaped like a disk. They saw that. But the first couple, the Herschel siblings, saw it as a disk of stars with the sun at the center. Then there was Captain, who also saw the sun at the center. And finally, who did we get?
Shapley.
What was his name?
Harlow Shapley.
Harlow Shapley. Okay, and he finally was looking at the globular clusters and he saw a spherical shape. So that's kind of what I'm talking about. The size was pretty small at first, and we weren't getting the real center. And then finally Harlow Shapley saw the real center and then got a good sense of how big the Milky Way was as well. So that's it. That's basically it. And I think I have it again right here. Explain how the Milky Way center was able to be located by Harlow Shapley using globular clusters. Where are the globular clusters located?
Halo.
In the halo. So they're not obscured by the dust, which is in the disk. You could see them clearly. And because of that, he had a nice picture that became a spherical distribution that showed him where the center of the Milky Way should be. Okay, what's the difference between population and population 1 and population 2? Population 1, what is that? New star or old star? New star. Population 1 means new star. It gets confusing. Generation 1 is not the same thing as population 1. So population 1 were the first stars that we studied, which are here really close to us in the disk. And they are new stars, young stars, okay, young stars. Do they have metal or not? Metal rich or metal poor? Metal rich, because they're not first generation. They're like third, fourth, fifth maybe. Metal rich, found in the disk, okay, young stars, okay. Population 2, old stars, found in the halo. Population 2 are old stars, therefore they don't have a lot of metal. They are mainly hydrogen and helium, okay, so old red stars. Population 2, metal poor, okay, metal poor. Low metallicity. Okay, describe the interactions among the galaxies in the local group. First of all, what is the local group? Did I put it on there? Local group? I did.
It's on there, you can cover it.
Oh, I forgot to cover it. Okay, what's local group mean?
It's all the galaxies close to
The galaxies that are closest to the Milky Way. It's a small number, you know, what did we say, 14? Okay, it's a small number. It could be 15 actually, but whatever, it's a small number. Yeah.
Did you say with local group, they don't expand like other
Okay,
galaxies?
so we just learned that the whole universe is expanding, but the local group is so close to us that they're not affected by this expansion. And so they're gonna stay with us forever, right? They don't get affected. And so I didn't go into a lot of detail on this, but the universe is expanding, but it turns out that on a small scale, it's not. So it's expanding between the galaxies, but not when you're right here in the galaxy. That's a little weird, but that seems to be what's happening. So this expansion of the universe doesn't seem to work within a single galaxy or even in the local group. But once you're outside the local group is where we see that expansion taking place. So we didn't go into that much detail, so you don't have to worry too much about that. But what's the interaction? What force is keeping the local group together? That would be gravity, right? This is the reason why Andromeda is coming to get us, or I don't know if it's get us is the right answer. We're going to get them too, right? So a mutual destruction? No, it's not destruction. It'll be a reformation, right? Will we be a spiral galaxy anymore? No. Well, I don't know. We could be. It depends on how. Probably not, though. Probably what will we get? Probably get an elliptical galaxy. But for a while, there'll be plenty of stars that are still alive. But eventually, it will settle down, and you'll see a nice elliptical galaxy there. Yeah.
Is Andromeda's tilt?
It is tilted. Yeah, it's tilted. That's why when we see it, we can actually see the face. Yeah, exactly. So we're like that. Yeah, exactly. So it's definitely going to make a mess. But probably no stars will actually hit any other stars. That's pretty wild, isn't it? No stars in Andromeda will actually run into any stars in the Milky Way. They will not actually hit each other. There's no like galactic Well, maybe there are, but you know, it's not the most common thing. Spaces are so big between stars that they could just interact and orbit each other, but never really hit. It's hard to hit, as a matter of fact. Okay, so what's going on though? The Magellanic tidal stream means that the little, large and small Magellanic clouds that are orbiting the Milky Way are being ripped apart by the tidal force of gravity from the Milky Way. And we can see those gases descending into the Milky Way. We can see it happening. So we're eating them up, right? They're eventually going to merge. Okay, Vera Rubin, oh, how do we see spiral? Oh, this is really good. Okay, so we talked about the concept of directly seeing or indirectly seeing. So you want to understand what I mean by that. The spiral arms are really the dark, not dark matter, sorry, the darker regions of our galaxy that are not lit up. We see stars at the edge of the arms, but the arms are the dark region of material that has not yet formed stars. So first of all, what do the new stars, the O and B association, show us? The edge. That's what they show us, the edge. Is it directly measuring the arm or indirectly? It's indirect, right? It shows us the edge. Where's the edge? Okay, well, where the new stars are. It doesn't actually show us that material that hasn't reacted yet, hasn't formed star. Is there a way to see this dark, cold matter? You're supposed to say yes, right? What is it? H1 and molecular clouds. How do you see them? With infrared, infrared for molecular clouds, and then radio waves, right? That's actually the one that they want you to know for sure. So the radio waves were detected coming from the cold H1 regions that make up the spiral arm. So we know where the stars will one day form. We know that, right? And the O and Bs are on the edge of that. So it kind of gave us a very consistent picture of what that arm looks like. We can't see it, right? But we know that it must be there because we see this pattern, right? See the big, expanse of H1, and then we see the edges, we see the O and B associations with them. So it's indirectly showing us where the edges. All right, so that's how we see them, right? We see them directly with the radio waves, indirectly with the formation of the O and B stars. Okay. How did Vera Rubin deduce the existence of dark matter? We kind of went over this, but what is the answer? She measured the rotation curves and showed that the stars at the edge of the galaxy were moving too fast. They should have been flung out. They should have gotten away. They're going too fast. And that meant that there must be more gravity than we would normally expect there to be. And so she said there's a halo of dark matter around the galaxy, which is preventing those things from escaping because gravity is strong enough to keep them in. Okay, machos, okay, and we talked about the machos. Black holes were machos, right? And we would have seen the flashes of light. They didn't show up, no machos. WIMPs are going to be hard to detect because they don't interact through the strong nuclear force. They don't interact through the electromagnetic force, right? We can't see them. So maybe I should have made that clear. Light is an electromagnetic wave. So matter that interacts through the electromagnetic force can be seen, right? Normal matter that you and I look at is interacting with light, which is an electromagnetic wave, which means it's interacting through the electromagnetic force. But matter that cannot be seen does not interact with the electromagnetic force. Neutrinos cannot be seen. They're too small anyways, but there's other matter, maybe like neutrinos are so ethereal. They pass through the earth without stopping. Dark matter can be all around us right now, and we just can't sense its presence. Okay, that'd be kind of weird, but that could be true. Although, wouldn't the force of gravity be stronger? No, because it's all over the place, maybe almost homogeneous. It wouldn't affect the gravity on Earth the same way. Isn't that crazy? All right, so we didn't talk about that too much, but it is pretty fun. Okay, so how is galaxy formation similar and different than solar system formation? So big cloud collapses to a smaller cloud. What happens to the rotation, for example? Speeds up, right? And what happens to the shape? Flattens out. What is the reason? What's the physics that is behind that? Conservation of angular momentum. So is that true in both solar systems and galaxies? Of course, it's beautiful. So conservation of angular momentum can explain the picture. So you get, what do you get? A central bulge, that's a star in a solar system. It's a galactic bulge in a galaxy around which you have a disk, right? That's the planetary, protoplanetary disk, which becomes a planetary disk of a solar system, which becomes the galactic disk for a galaxy. So those are similar. That's good. What's not the same? One big thing, for sure. One big thing. The velocities, right? What should happen in a solar system? The further you get from the star, the slower the planets have to move because gravity is getting weaker. But the difference with galaxies is that the further away, they don't slow down. That means that the gravity is not getting weaker. So with galaxies, we need to talk about dark matter. Do we need dark matter to have solar systems? Apparently not. So dark matter doesn't seem to be a problem for solar system-sized objects, only with bigger things like galaxies. Okay? So far, so good. Memorized now? And I think we've gone over these numbers already, but the size of the Milky Way, diameter, 30 kiloparsecs, 100,000. Oh, I forgot this, right. At the edge, not in the center, at the edge, the thickness of the Milky Way is about 2,000 light years, 0.6 kiloparsecs. And the halo is about the same as the radius or the diameter. It's just a spherical shape, about 30 kiloparsecs. The galactic bulge is 10 kiloparsecs, 1/3 of that. We're on the Orion Cygnus arm. I did put that in there. Okay. We're on the Orion Cygnus arm, about 8 kiloparsecs from the center. And the sun goes once around every 233 million years. Okay, that's just cute. I don't know if I'll need that much more. The mass of Sagittarius A, the supermassive black hole, is about 4 million times the solar mass. And in the Milky Way, we think that there's 10 to 1. No, 9, that's not right. 1 to 9. 9 to 1. There should be 10 times as much matter as we can see. That's what I want to say, right? But there's 90% of the matter supposed to be dark matter. Okay, 90% dark matter. That's pretty crazy. Why should that be? I don't know. So that we can have enough gravity, right? Alrighty, so chapter 16. It's going too fast, huh? Are you guys okay? Is everybody good? Yeah, okay. So chapter 16, spiral nebula. Okay, so why did I say spiral nebula? Where am I? Where am I in time? Am I in the current day? Clearly not. I'm going back in time to before the 1930s. And at that point, we didn't know that there were other galaxies. We didn't know. We just saw stuff, right? There's a bunch of stuff. And the spiral nebula were examples of things that we couldn't really explain very well. They're spiral in their shape. They're kind of interesting. But to be honest, no one could really explain how they would form. How do you make a gas cloud have such a beautiful pattern? That's pretty weird. But there was a lot of debate whether that was inside the Milky Way or outside the Milky Way. Was it a part of the Milky Way and this is the whole universe? Or was it just one of many galaxies? The Milky Way is just one of the many, right? So there's the many galaxies or the one galaxy. And that's called the Great Debate. Okay, before I get to that, let's talk about make a list right here. So grand design spiral, it's just a tiny little thing, right? What do you say? You can see the spiral arms all the way from the center to the edge. There's no breaks. They're beautiful. They're kind of pretty. They're pretty, right? I don't know, it depends on your taste in beauty, I guess, too. But you can see the arm all the way from the center to the edge. A flocculent spiral has breaks in it. And so that might just be, well, it's just timing pretty much, but for whatever reason. They may be in the process of forming as well. That could be what we're seeing, different stages. We didn't worry about that in our class. A barred spiral is a spiral galaxy which has an elongated, a bar in the center, and the spiral arms come out of the end of the bar. What's most important about that is how did the bar form? I gave you a logical explanation that I want you to be able to pair it back to me, okay? And the answer is tidal forces, right? Galaxies, even if they get close to each other, can affect one another with their tidal forces. So a barred spiral might have originally been a regular spiral, but being too close to another galaxy stretched it out. Okay, I told you you need to know elliptical. What's elliptical? Yeah, it's a spherical, but stretched out usually, elliptical, ovoid kind of shape. Okay, you don't have to know CV and lenticular. I should have taken those out. Don't worry about those. Those are like tiny little details. Don't worry about it. I'm just going to leave it out. Okay. I don't have any questions on those. Okay, no questions on CD. Let's take it. Hubble had this idea that galaxies are evolving, and you're supposed to know what he thought. Which ones were the youngest galaxies according to Hubble? The elliptical galaxies. The perfectly spherical elliptical galaxies were the youngest. And then they evolved into two possibilities. What were they? A regular spiral or a barred spiral. They could go two different pathways, and we call that the tuning fork. So the tuning fork was Hubble's idea on the evolution of galaxies. Turned out to be wrong, but anyways, you want to know what that is. Okay, what's a megaparsec? Megaparsec?
10 times 6 to the
Million parsecs, right? Megaparsec. He's trying to say 10 to the 6. Yeah, 10 to the 6 parsec. Mega. 10 to the 6 parsecs, okay? And Hubble, why is Hubble important in this story? What did Hubble do? He settled the Great Debate, right? I think I have some stuff down here on Great Debate. But the Great Debate was whether or not the galaxy was just what we see, one big galaxy, or many, many galaxies. And Hubble settled the debate. And anybody remember how he did that? By looking at Andromeda Galaxy. And he found, he was lucky. He got lucky. He actually really got lucky. He was up all night. He got lucky. And he saw, you guys get that little, anyway, okay. He looked at, he got lucky, he found some Cepheid variable stars, right? So because he knew they were variable stars, and he knew about the relationship with variable stars, the longer the period, the greater the luminosity, he was able to calibrate that using the, calibrate the distance to Andromeda, and he found that it was, how far? He said, at least 1 million light years away, right? That's pretty crazy. So it wasn't in the Milky Way anymore. There's no way that that could be in the Milky Way. For the first time anyone was able to measure the distance to the Andromeda Nebula, Hubble, he discovered that it really couldn't be inside of our Milky Way anymore. It's not the right size. Okay? It doesn't fit. Remember who told us the right size? Who gave us the right size of the Milky Way? Who finally figured it out? Harlow Shapley, right? Harlow Shapley, when he found the diameter of that sphere, he figured out the size of the Milky Way, 30 kiloparsecs. Up until that point, we didn't know the right size. But that size is only 100,000 light years. 1 million light years is way bigger than that. It's 10 times as far. So Shapley, hey, this whole thing is about 100,000 light years. Hubble says, well, that thing is 1 million light years away. It can't be inside of the same thing. They're not the same. That's a big deal. Okay. So what we did at that point is, now we're jumping to, we get that, right? The Milky Way is just one of many galaxies. We stopped calling them nebula, now they're galaxies, right? So that was a big turning point in astronomy. But in order to try to progress further, we wanted to find the distance to further and further objects. And so we created a ladder. And we call it the cosmic distance ladder. So I skipped over the word calibration, but it is an important word. What do we mean by the word calibration? How do you calibrate a technique? So the answer is,
get it more precise.
well, okay, but but what? Well, calibrate means to make it work. To calibrate it. It doesn't work until you calibrate it. The calibration step is when you add another step to the ladder, it has to connect to the step that came before. And so you have to be able to use the two techniques to measure the distance to the object. So what is the first technique that we use to measure the distance to stars? Parallax. Parallax. You need to know that, right? That's the only good for the closest stars. So the closest stars, you find the distance by using parallax, right? Remember the idea with parallax. They shift as the Earth goes around the sun. We see them changing position. And that allows us to measure the distance to the nearest stars. Only about 1,000 parsecs, 3,000 light years, not very far. In order to do the next step, you need to be able to take a star and measure its distance with parallax, as well as this new technique, which is called spectroscopic parallax. You're supposed to know them in order. So I mean, go through the order. Parallax, spectroscopic parallax, Cepheid variables, the Tully-Fisher law, type 1a supernova, and finally the Hubble's law, right? So those are the correct order. On the ladder, you connect it to the step that came before. You calibrate it. And the way you do that is by using both techniques with one object. That's called calibration. So then the next step agrees with the step that came before. It's calibrated. That's basically what it is. So you don't have to know specifically how far each one goes, but just know the correct order, right? Okay. Which one do I not like very much? Do you remember? The Tully-Fisher. Okay. That one has to do with rotation curve, and it's really bad. It's really bad. I mean, like, why would you even want it? But it's good for the situations when you can't use something better. Okay. Cepheid variables, we already talked about that. You want to talk about it some more? Maybe I should mention it, right? What do you know about Cepheid variables? Variable stars change their brightness, and it can be a few days up to a couple of months, right? Maybe even 3 months. And what happens is the period, the time it takes between being bright, dim, and back to bright again, right? That time, it tells you what the luminosity of the star is. So the longer the period, the greater the luminosity will be, right? That was the relationship. A Tully-Fisher examines the rotation curves of galaxies. And when you study the rotation curves, you're trying to estimate the fastest speed of the stars that are on the outer edge of the galaxy. From that number, you can figure out, or you can model and estimate the number of the mass of that system. From the mass, you can estimate the total luminosity. Again, it's not very good. I mean, really think about all the problems. I can think about all the problems. You don't have to worry about that. But you should understand it's just really a difficult one to do. Anybody think of one reason why it's difficult? Why do you think it would be so difficult? Even if you know the right mass. Anybody think of a confounding problem? What's one of the problems that you might have?
Maybe we started with this.
If you know the speed of stars on the outer edge of the galaxy, why could you still have trouble estimating how much light comes out of it? The age is a problem, right? What if it's a young galaxy? You've got lots of bright stars shining, but as soon as they die out, they're not shining anymore. So it's like the age of the galaxy will affect the light out, but they do include that. That is actually one of the factors, but it's just a really tough thing to do. So I don't like it very much because I think that it's not very reproducible. That would be one of my problems with it. But I do love this one. I love this one. I think this one you should also love. Type 1a supernova. So what's a type 1a supernova? We know how to do it, right? What happens? Start with a white dwarf. But in order for it to be a supernova, what does it need? It needs a companion. Now, it turns out we have learned that it doesn't have to be a red giant, but that was the one that we used the most. But it turns out different companions will actually work. So it's pretty good. But let's worry about just the one that you have to worry about. White dwarf, red giant companion. The white dwarf steals a little bit of matter, and every time it does, what happens? A flash called a nova, right? It happens over and over again, but every time you add a little bit of mass to the white dwarf. But the white dwarf cannot exceed the Chandrasekhar limit. On the day that it does, it won't be strong enough to hold back gravity anymore. It will collapse all at once. So a type 1a supernova is always 1.4 solar masses and always has the same amount of light coming out of it. It always has the same absolute magnitude. So it is a standard candle because of that. So standard candles have a known magnitude, absolute magnitude and luminosity, right? And you compare the absolute magnitude with the apparent magnitude, and what do you figure out? The distance. You find the distance. Okay, the Hubble's law is also amazing, really cool, and it comes from the fact that if you go beyond the local group, what's true about all the galaxies? They're moving away. Every galaxy is moving away from our galaxy because the universe is expanding. The universe is expanding. So the Hubble's law says that the further away you go, the faster the galaxies will be moving away from us. It's directly proportional. And I asked you to memorize, it's going to be down here a little bit. The Hubble constant is the constant of proportionality. And we learned today the number, what is it? 69, okay, easy number, 69 kilometers per second per megaparsec. Okay, so that's the value. So if I write it down, you should be able to recognize it. Okay, so if it's one of the multiple choice answers, you know what it is. Okay. Active galactic nuclei are really bright objects that are coming very, very far away. They're really, really far. The most distant things we've been able to see. The reason we see them is because they are so incredibly bright. Each one, when it has a burst of energy, is like 1 billion stars all at once, right? It's just huge burst of energy. What is the unified model? Oh, it is unified model. What is a unified model? So active galactic nuclei is a galaxy which has a lot of energy coming out of its center. Active galactic nuclei. It can be light and in the form of radio waves or other kind of energy. It can be jets of energy shooting out of it. It can be just visible light. That's what the quasars were, visible light. Or it could be jets, right? This is something called, what did we learn about? What's it called? That's a funny name. What's the name? A blazer, sorry, a blazer. A blazer is a superluminal jet coming out of the galaxy. Superluminal means faster than the speed of light. So is that possible? Not supposed to be. And probably it's not really faster than the speed of light, but it has the appearance of moving faster than the speed of light. The only way you're allowed to do that is if you talk about space-time expansion, and then it's okay. But actually, if you just have normal inertial reference frame, special relativity says, no, you can't go faster than the speed of light. It's not possible. So anyway, safer galaxies are radio galaxies. And there's 2 types, right? And do we worry about that? Type 1 were broad lines, broad absorption lines, and type 2 were narrow, right? So type 1 were hot galaxies, type 2 were cool. And the unified model. So what's the unified model? Let me just go ahead and draw a little picture for what you should have in your head for the unified model. Okay, it's supposed to be a nice, simple picture. What's in the center of the model? Center of the model. What do you have inside of your active galactic nuclei? What's driving it? A supermassive black hole. Called SMB, supermassive black hole. Is that the center? In order for it to function, it has a powerful magnetic field. In order to have a magnetic field, what must be around the supermassive black hole? What do you need? Spiraling around. You need an accretion disk. So there is a disk of matter which is spiraling around, the accretion disk. Okay? Now, the accretion disk is going to generate the powerful magnetic field, which will lead to something else. What will come out of this? You will get jets, right? Both above and below. The jets that come out are because of the magnetic field, which is formed because of the accretion disk around us. But sometimes when we look at the hot gases in the accretion disk, they don't look so hot. And so what we hypothesize is that around the accretion disk, there is a torus, or a donut shape of material. And so if we look from this side, we can't see the hot gases. And so what we see are cool gases, relatively cool gases. This is the type 2 Seyfert galaxy. If you look here, and you can see the hot gases in the accretion disk, that's a type 1 Seyfert galaxy. And if you look along the jet, and you see that jet coming right towards you, we call it a blazer. Okay? So anyway, so these are things that you're supposed to realize. So the key thing is that the one model can look like all of the different active galactic nuclei that you've seen. One model can show all of the different signs. Quasars, blazars, Seyfert galaxies, everything can be explained with that's a jet. Okay, jet shooting out. That's about it. Okay, that good? To go real deep, it's just, what does the picture look like? What are the pieces, and then how does it work? Okay, so and again, not very detailed. Okay, so be able to describe the great debate. We kind of talked about this. Harlow Shapley, what did he think? He's the guy who came up with the globular clusters. What did he think? The Milky Way is everything, right? Everything we can see is just the whole universe, right? There's only one, and it's here. This is it. And then Huber Curtis, Huber is, I misspelled it. Huber is his name. What did he think? Milky Way is just one of many galaxies. He was the right one, right? He was correct. What is the major difference between spiral and elliptical galaxies in topology, which means shape, and also the rate of star formation? So what did we say about spiral galaxies? Do you see young disks, right? So what color do we call them? They're bluer because you have young stars forming there. So they really look bluer when you take a photograph. So blue disks, right, means younger stars are forming and they're disk shaped. And then elliptical galaxies are red and ovals or spherical, stretched out spheres. Okay, they're reddish. So what about elliptical galaxies? Do they form new stars? No new stars, right? Do they have anything better than, anything more than spiral galaxies? Anything special? They have more of these, what are they? Globular clusters. Well, that makes sense because they formed from the merger of spiral galaxies. So they took on the globular clusters from the first one and the second one, and maybe more, and they combined it into one. Those are whizzing around in all different directions. How does Hubble's original tuning fork, what does it look like? Starting with elliptical, gradually evolving into spiral or barred spiral. He was wrong. He got it backwards, right? The spirals turn into, actually spirals turn into barred spirals when what? When they get close to each other, right? When they interact with other galaxies. And then when they merge, they form elliptical galaxies. So he really got it wrong. Okay, and we just described the major components of an AGN, okay? The unified AGN, okay? Got it? So what is it? Supermassive black hole, accretion disk, the torus, and the jets. That's it. Those are the pieces. 1/3, oh, memorize this, right? Oh, I forgot to tell you this. Yeah, 1/3 of them are barred. And what are the rungs? And you want to go through this again? What are the rungs? Step 1, parallax. Step 2, spectroscopic parallax. Step 3, Cepheid variable. Step 4, Tully-Fisher, not so great, but whatever, we got it. Step 5, type 1a supernova. And step 6, the best one of all, the Hubble's law. Okay, those are the 6 steps that you need to memorize in the right order. And the current value, 69 kilometers per second per megaparsec. I'm done. Okay, but we can do the questions again if you want. Should we do them again? You have questions? Should we? Anybody have questions? How about first people? Anybody with questions? Okay,
Go over O and B association.
Sure. The O and B associations are the idea that we can't see all of the spiral arms directly. Sorry, we can't. Okay. Sorry, when we see the spiral arms, we see some of it is direct, and that's coming from the radio waves being emitted by the cold H1 gases. Right? So they haven't formed stars yet, but they will. But O and B association is the idea that a hot young star, O and B, just formed. Why? Because they can't live very long. And where do they form? At the edge of the spiral arm. Where there's gases available, the shock wave hits that and forms a star. Right? So where we see those stars forming, we think that's the edge of the spiral arm. So the O and B association means that they form at the edge of the spiral arm. There's an association of the location of those O and B stars with the spiral arm itself. That's it. O and B association.
And then we don't think about the 180s they're going to redshift. That's like they're accelerating.
So what?
The 180, the supernovas, it's the redshift, so they don't have a lot.
Wait, 1A, 2 types of super.
Yeah, supernovas.
Yeah.
They're redshifted.
Okay. Why are they redshifted? Because they're coming from galaxies that are
They're
redshifted.
moving away.
But we can figure that out. We still identify almost like supernovas. So we take that into account, but the brightness of the type 1A is what we use to determine the distance. Right? The absolute magnitude is known. We compare it to the apparent magnitude. So the color shift doesn't change the total energy output. Right?
That's how Hubble's law was derived.
Oh, how Hubble's law
From
was
the
derived.
redshift of the supernova.
It was not from the supernova redshift. It was the redshift of the galaxy's light itself. The whole galaxy spectrum was taken, and the redshift of the galaxy was determined.
But the more recently they have done.
So now we know that we could do that. We could do what he said, but he didn't see that. He just looked at a single point of light that turned out to be a galaxy, and measured from that single point of light a spectrum. And what they saw was that spectrum changed depending on where he was looking. So he was able to determine those galaxies must be moving away. So you know what, actually, as a matter of fact, he started with the 70 variables. Those were the first things he looked at. He must have been looking, the overall shift of the galaxy. You know what, I know he could see there were galaxies, that's right. He didn't see them as points, that's wrong. He saw them as galaxies. But what he did is he looked at the center of the galaxy, which should show zero shift, and it was shifted. Right? This is a typical galaxy, and it doesn't look like a typical galaxy because it's been redshifted away from it. So what he did is he saw that there was a shift in the central part of the light, which came from the galaxy. That gives him the Doppler shift from the galaxy itself receding. And then he would see on top of that the rotation. So that would be direct. I'm sorry, that other influence.
Okay, so I get that.
So the light at the center of the galaxy is probably what you watch.
So how does like the more recent stuff, like say happening, like supernova, trying to figure something out?
Wait, so that I'm not sure.
So the universe expanding, they're like, oh, but it's also accelerating.
Oh, okay. So, but that's what that's measuring the Hubble constant. It's been great having you in the class. I know you're not going to come, right? Have a wonderful summer, okay? You were a very good student, thank you. Okay, so the answer is that we've been trying to watch with the expansion and try to measure the speed of expansion. There was a lot of debate about what's happening. Is the universe going to continue expanding? Or will it slow down, stop, and then squish back together a big crunch? And what they came up with is that the expansion rate seems to be growing. So in fact, something is going on. Something is pushing the galaxies apart, not just letting them expand and slow down. Gravity should be slowing them down, right? But it's not. In fact, it seems to be accelerating. So what we have decided, we've invoked, is this idea of dark energy. With dark energy, is the we didn't cover that.
So we didn't
cover dark
that's
energy.
what I think. So
Dark energy would be the reason when there are galaxies are expanding away from each other with a greater rate. And so Einstein actually may have come up with the answer. He said in his field equation that he said there's a certain constant that should be whether there's something there or not. And so as the universe expands, it's like it fills itself with this constant. And that is causing this additional pressure, which pushes the galaxy. So it's like an anti-gravity.
But it has a relationship with the Hubble constant.
I'm sure the Hubble constant is going to change as a result of that. Change at all. Right? It's a constant. At this moment, it isn't Hubble. And what will happen is, over a very long time scale, that constant will change. So this is a really, we have, but this is part of the problem. When we talk about then that expansion rate should continue to slow down. It's not slowing down. So that means that something is maintaining. I don't have to go to it. We don't know. I mean, whenever we say dark, we don't know the answer. Like, hello, I don't know what's doing it. Something's doing it. Yeah. So you want to do the questions? You have questions? Yeah. Okay, sure. Let's talk about. So, two types of relativity.
relativity.
Yeah. So two types of relativity are special and general relativity. Special relativity is when things are moving very fast. They have to be moving very fast.
Not observed, it doesn't.
When things move very fast,
That's the reason.
we find out that the clocks don't tick the same way. The whole measurement of time changes when you move very fast. So in special relativity, the clocks tick according to the speed of the object as it's seen. So you and I will always experience normal time, like my heart beats, just like normal. I can never tell that my heart is acting funny. But if I were on a rocket that was moving very fast, the people on the rocket, again, have no sensation that anything is going on. They feel normal. But if we watch them, the faster the rocket goes, the slower their clock appears to tick. We would see their clock ticking slower than our clock. And so if they measure a year going by, we're going to measure much more than a year going by. This factor gamma controls how much time is being dilated. So a factor of 100 or more, right? Or 100, let's stick with 100. If 1 year passes for them, 100 years would pass for us. And this is because we see light traveling with a constant speed, no matter who is watching it. So this is one of the reasons that it works, right? I showed you how to derive it, that we see the light traveling further. It must be that more time is passing for us. So there's three things. Let me tell you the three things. One of them, time dilation. For the people on the rockets, they will see the distances shrinking, length contraction. And then the third one is the mass appears to have more mass when it's moving fast. So the rest mass stops being the same, and that mass appears to be larger the faster the object goes.
I did the same one.
So again, it's enhanced by the factor gamma.
I guess I read it fast.
So if it's 1 kilo when I hold it in my hand,
Yes, observe.
and then it moves really fast, it now looks like it's 100 kilos. It has more mass effectively.
When you go
Right to left.
They're all connected. That's all special relativity. Yeah. Now, general relativity is not fast. It's gravitational field or acceleration.
everything increases.
The greater the gravitational field, or the larger the acceleration,
Okay, the sun mantra.
the slower the clock will appear to move.
It's 99%.
So you and I, we don't experience it, but it turns out you can measure it. And we showed the picture, or we actually didn't talk about it too much.
So this is.
You can take a clock to the top of a mountain and compare it to a clock at sea level, and they do not tick at the same rates because of general relativity. So which one has the stronger gravity?
And then it continues.
At sea level. So then the one at the top of the mountain is less effective than the one at sea level. So if you're at the top of the mountain, you're going to say your clock is normal, but when you look at the clock down here, what is it going to do? Tick slower. Yeah, that's right. And the further away you go from the Earth, the less you're affected by gravity. But it turns out you can also use acceleration. The greater the acceleration, the slower the clock will tick. So even if it's a rocket accelerating with a great acceleration, the same thing is true. The greater the acceleration of the rocket, the slower we will see the clock ticking. That's another way that this will manifest itself. But what else did Einstein say? Light should be affected as well. Light is affected by gravity as well. Okay, so there are two major things to talk about: time dilation and gravitational redshift. So we just mentioned time dilation. The greater the gravitational field or acceleration, the slower the clock will appear to be ticking. And the second one is the light that is escaping from a massive object will be redshifted. It gets a redshift. We call it the gravitational redshift. It's not the Doppler effect, but it gives you the same kind of effect. It shifts to a lower frequency.
And then
more
more
than
than
I
put it at the white dwarf stage, then it's like.
It's gonna be the size of Earth.
So general relativity comes from the curvature of space-time. Yeah.
This trip to me.
Is that kind of good? You okay? Yeah. Those are the two main things. Are you guys talking about the questions or no?
We're talking about the most missed questions from exam 3.
Oh, okay.
Is that okay?
Did you get the questions that I gave?
From Riley.
You did. Okay, good.
I have to look
What was that?
them up because
Because
I,
I thought that it.
It's not
Oh, you had it in that, okay, so that's gonna head over there right now.
It's moving.
it's not moving, it's,
What's that?
Because I thought it was a trick question, like it's. trying to
Yeah,
say-
no.
It'll
So
fix
I
by
thought
tomorrow, yeah,
lots
don't
of
worry.
sources.
Okay, so I guess I'm ending the live stream. Yay, we finished early again. Woohoo. Wahoo!